The method of partial fraction decompositions is all about taking a complicated rational function, like the one we have here, and rewriting it, breaking it down into simpler rational functions, which we can easily integrate. So this method involves heavily the method of linear algebra, solving systems of linear equations, and row operations. So if you want, I highly suggest this. Pause the video now, go back into the algebra notes and look at the section concerning solving systems of linear equations, and make sure that you're familiar with the essence of matrix algebra, linear equation solving, and row operations. So we'll go through all the details in this one example, and I will skip the finer details in later examples. Now, our whole job is to integrate this rational function, x squared plus 4x plus 1 divided by x squared minus 1 and x plus 3. So I'm going to ignore the integral now and just work on simplifying the integrand. X squared plus 4x plus 1 over x squared minus 1 and x plus 3. So our first job is to factor the denominator as much as possible. The x plus 3 is already in its simplest form, but the x squared minus 1 can be broken down further as x minus 1 and x plus 1, which I will write as x plus 1 times x minus 1. Okay. Now, each one of these linear factors will get its own fraction. So we have some unknown numerator over the x plus 1. And then we have some unknown numerator over the x minus 1 factor, and some unknown numerator over the x plus 3 factor. It's kind of like us getting a common denominator, just in reverse. We're going backwards. So now we'll get a common denominator on the right-hand side and see what that implies about our unknown constants a's, b's, and c's. This is our goal, to figure out what a, b, and c have to be. So I'll take my first fraction, a over x plus 1, and I will give it an x minus 1, top and bottom, right? Because I don't want to change anything. I'll also give it the other denominator, x plus 3, top and bottom. So now notice this denominator is my desired denominator. And I'll do the same thing for the b term. I'll take b, and I'll multiply it by the x plus 1 and the x plus 3. Now its denominator is x plus 1, the original x minus 1, and the x plus 3. We'll take c and multiply it by the denominators that it is missing, x plus 1 and x minus 1. Now that we have the same denominator, we can write it as one giant fraction. And multiplying through, right, sending the a through and performing all of our distribution, we end up with a numerator equal to ax squared plus 2ax minus 3a, a plus bx squared, a plus 4bx, and a 3b, along with a cx squared minus a c. So this fraction is supposed to be equal to this fraction. The denominators are the same, which means that the numerators have to be the same. Therefore, x squared plus 4x plus 1 is equal to this numerator right here. And I'm going to go ahead and combine like terms. So how many x squareds do we have? We've got this ax squared. We also have this bx squared. And also this cx squared. So I'm going to need a little bit more space. I've got a plus b plus c x squareds. So now let's look for the x's. How many x's do we have? 2a of them. Oops. We also have 4b of them. And that's it. That's all of my x's. So now let's move on to the constants. 1. We have minus 3a. And we're missing a 3b and a minus c. So you're really just matching up coefficients. You're looking at how many x squareds you have on your right-hand side involving your unknown coefficients, a's, b's, and c's, and how many x squareds you're supposed to have. So this allows us to set up a system of equations. You have 1 x squared, so 1 has to be equal to a plus b plus c. You have 4 x's, so 4 has to be equal to 2a plus 4b. And you have 1 constant. So that tells you that 1 has to be equal to 3b minus 3a minus c. So let's set up the system and go through it. Writing these 3 equations down, we've got a plus b plus c is equal to 1 from our x squareds. 2a plus 4b is equal to 4 from the x's, and a minus 3a plus 3b minus c needs to be our constant 1. Now, solving this via row operations, so I'll multiply my top equation by minus 2, and then I will add it to my second equation, replacing my second equation with it. So again, if this is foreign to you, go back into the algebra notes and look at the section concerning solving linear systems of equations. But after doing so, we are left with the following system. Now, my next step is to get rid of the minus 3a. I'll do so by multiplying my top equation by 3, adding it to my third equation, and then replacing my third equation with the result. After doing so, we are left with a plus b plus c equaling 1. I will also take my second equation, just divide by 2, make it a little bit easier on myself. I have b minus c is equal to 1. And my resulting third equation is 6b plus 2c is equal to 4. All right, the next step, I am going to multiply my top equation by minus 6, add it to my third equation, and replace my third equation with it. So I have my first equation untouched. I have my second equation untouched. And the resulting final third equation is 8c is equal to minus 2, which we can now just waterfall that backwards. My third equation solves c as minus 1/4. My second equation solves b as 3/4. And my my first equation solves a as 1/2. So these are what the constants have to be in order to make this decomposition work. So let's go into this. We are finally going to rewrite the integral. The integral of x squared plus 4x plus 1 over x squared minus 1 x plus 3 can be decomposed as 3 different fractions. A, which is 1/2, over x plus 1, plus b, which is 3/4, over x minus 1, and then plus c, which is negative 1/4, over x plus 3. And each one of these can be easily integrated using a natural log. This becomes 1/2 natural log absolute value x plus 1 plus 3/4 natural log absolute value x minus 1 minus 1/4 natural log absolute value x plus 3. So we took a complicated rational function, we broke it down into 3 unknown rational functions, and then we just ran that backwards to figure out what the numerators had to be. And then we were finally able to decompose our original integral and then finally integrate.